Welcome to this lecture on the traffic flow model. Today, we are going to explore how the mathematics of partial differential equations can explain the everyday phenomenon of traffic jams. We will see how treating cars like a flowing fluid allows us to predict exactly when and where congestion will occur. Now that we know our topic, let us understand the perspective we must take. Imagine looking down at a busy highway from a helicopter. From up there, you do not see individual drivers making unpredictable choices. Instead, you see a continuous stream of metal and glass that behaves almost exactly like water flowing through a pipe. This is called a macroscopic model. By treating cars as a continuous, compressible substance, we can use the mathematics of fluid dynamics to describe how invisible waves of congestion form, move, and eventually dissipate. This approach is incredibly powerful for predicting large-scale traffic patterns. To build our mathematical model, we first need to define our core variables. This simple multiplication is the foundation of our entire model. Here, Q represents the traffic flux, which is the rate at which cars pass a specific checkpoint. Rho represents the traffic density, or how tightly packed the cars are on the road. And V represents the velocity of the vehicles. If density increases while velocity stays the same, the flux goes up. For example, if you have 50 cars per kilometer traveling at 100 kilometers per hour, exactly 5,000 cars will pass your observation point in one single hour. With our variables defined, we can establish the core physical principle holding the model together: the conservation of cars. Conceptually, if there are no exits or entrances on a stretch of road, cars cannot simply vanish or appear out of nowhere. The integral on the left side counts the total number of cars currently located between point A and point B. The time derivative outside measures how fast this population is changing. On the right side, we calculate the net flow by taking the flux of cars entering at point A and subtracting the flux leaving at point B. If more cars enter than leave, the total number inside must increase. This integral equation leads us directly to its differential form, which is a classic first-order non-linear conservation law. We get this by bringing the time derivative inside the integral. The first term represents how the traffic density changes over time at one specific spot on the road. The second term represents how the traffic flow changes as you move forward along the length of the highway. Physically, if the flow decreases as you move forward, meaning the cars ahead of you are slowing down, the density must increase over time. This mathematical relationship guarantees the formation of a traffic jam when flow drops. We know that human drivers naturally adjust their speed based on how crowded the road is. The Greenshields model captures this behavior mathematically. In this equation, Vmax represents the absolute speed limit drivers choose when the road is completely empty. Rhomax represents the jam density, which is the bumper-to-bumper condition where cars cannot move at all. Notice how the formula works. When the actual density rho is 0, drivers travel freely at maximum velocity. As the density approaches the jam density, the fraction approaches 1 and the velocity drops linearly to 0, bringing traffic to a complete halt. Now, let us combine what we have learned. By substituting the Greenshields velocity model into our basic flux equation, we get a new formula for the total traffic flow as a function of density. Because we are multiplying density by a term that also contains density, we create a downward opening parabolic curve. This tells us something fascinating. The flow is exactly 0 in two extreme situations. First, when the road is completely empty, and second, when the road is completely jammed. Between these two extremes, the flow must rise to a peak and then fall again as crowding forces drivers to slow down. This diagram perfectly visualizes the parabola we just derived. On the horizontal axis, we have traffic density, and on the vertical axis, traffic flux. You can clearly see how adding more cars to a busy highway actually makes the situation worse. Once the density passes the peak of the parabola, the optimum density, the total flow drops dramatically. This happens because the decrease in vehicle speed outweighs the increase in the number of vehicles. This peak is the mathematical tipping point where smooth traffic collapses into stop-and-go congestion. The slope of the tangent line shown here represents the speed of the traffic waves. That tangent line on our graph brings us to the concept of kinematic wave speed. Here, the term C of rho is defined as the derivative of flux with respect to density. It is extremely important to understand that this is not the speed of the physical cars themselves. Instead, it is the speed at which a traffic wave, such as a ripple of red brake lights, travels through the stream of vehicles. Depending on the density, this derivative can be negative, meaning the wave actually travels backward against the flow of traffic. This explains why traffic jams propagate upstream, away from the initial bottleneck. Before we move on, let us see this with a concrete example. Imagine a major highway with a maximum speed limit of 120 km per hour and a jam density of 200 cars per kilometer. During rush hour, the density is 150 cars per kilometer. We want to find the speed and direction of the resulting traffic wave. First, we expand the Green-Shields flux equation into a simple polynomial. Then, we apply the power rule from basic calculus to find the first derivative. Notice the factor of 2 that appears. This means the wave speed decreases twice as fast as the actual car speed does when the road gets crowded. Continuing with our calculation, we now substitute our specific numerical values into the wave speed equation we just derived. We plug in 120 for the maximum velocity, 200 for the jam density, and 150 for our current observed density. Multiplying this out gives us 120 minus 180. The calculated wave speed is negative 60 km per hour. The negative sign is the most crucial part of this answer. It means the traffic wave is traveling backward, moving against the flow of the physical cars at 60 km per hour. This perfectly explains why you can suddenly hit a standstill traffic jam miles behind a cleared accident. Now, let us tackle another problem using the exact same highway parameters. We want to find the specific density at which the highway carries the maximum number of cars per hour. In calculus, to find the maximum of a function, we set its first derivative to 0. Since the derivative of flux is the wave speed, we set our wave speed equation equal to 0. By solving this algebraic equation for density, we arrive at a very elegant result. The maximum flow always occurs when the density is exactly half of the absolute jam density. This tells engineers that a road is most efficient when it is exactly half full. Now that we have our formula for optimal density, we substitute our specific highway's jam density of 200 cars per kilometer. Dividing by 2 gives us an optimal density of exactly 100 cars per kilometer. If the density stays at this number, the highway processes the maximum possible number of vehicles. With the optimal density identified, we plug it back into the original expanded flux equation, along with our maximum speed limit of 120 km per hour to calculate the peak capacity of this specific stretch of highway. Completing the arithmetic, we multiply 120 by 100 to get 12,000 and subtract the second term, which simplifies to 6,000. The final calculation reveals that the maximum capacity of the highway is 6,000 cars per hour. This is the absolute upper limit of what this road can handle. If more than 6,000 cars attempt to enter the highway per hour, the density will inevitably push past the optimal mark. When that happens, the flow will drop and a severe traffic jam will begin to build up rapidly. So, we have proven how traffic behaves mathematically. This brings us to why this matters in the real world. The traffic flow model is absolutely essential for civil engineers. It explains the frustrating phenomenon of phantom traffic jams, those jams that seem to appear out of nowhere with no accident in sight. By understanding that traffic behaves like a compressible fluid, engineers can implement ramp meters, which are those stoplights on highway entrances. These meters control the flow of entering vehicles to keep the overall density just below the critical threshold we just calculated. This ensures the highway operates at its maximum capacity and prevents backward traveling shockwaves. We have covered the full topic of the traffic flow model. Let us review the key takeaways. First, we learned that traffic can be accurately modeled using a first-order partial differential equation that tracks density over time and space. Second, this model works by combining the strict physical conservation of cars with a mathematical rule for how human drivers adjust their speed. Third, we discovered that traffic waves can actually travel backward, causing phantom jams. And finally, we proved that maximum traffic flow occurs at moderate densities, meaning pushing too many cars onto a road actually reduces its overall capacity. You now have a solid mathematical understanding of traffic dynamics.